Hello and welcome. In this video, let's explore neural networks. It is a fundamental of modern machine learning and AI. We will break down and go through the fundamentals. Frameworks like TensorFlow and PyTorch make it easy to build complex models. However, masterizing the fundamentals will give you a deeper understanding and provide long-term benefits in building and optimizing neural networks. Here is an overview of this video. We will start by exploring forward propagation. Forward propagation allows the neural network to make predictions. Next, we will introduce the chain rule, a crucial mathematical concept that forms the backbone of backpropagation. Next, we will dive into the backpropagation. It enables the neural networks to update their parameters based on the prediction error during the training process. Finally, we will enhance our knowledge by implementing a simple neural network from scratch. I tend to make this video simple and only focusing on the crucial parts. Follow along step by step, and by the end of this video, you will have a solid understanding of neural networks. Starting with this simple neural network, we have two input features x1 and x2 as the input layer, two neurons in the hidden layer, and one neuron on the output layer. Connections labeled from W1 to W6 are associated weights. Those weights are randomly initialized. They determine the strengths and the directions of the signals. The bias term is typically added to each neuron to adjust the output. We will simplify things for now by omitting the bias term. The bias works similar to weights, but excluding it can help us focus on the core mechanics without unnecessary complexity. In order to calculate the output of the first hidden neuron y1, we take the weighted sum of the input x1, x2 and weights w1, w3. The process applies to the second hidden neuron y2. After we calculate these weighted sums, we pass them through an activation function. There are many different activation functions that can be used. We will use a sigmoid function. Activation functions introduce nonlinearity into the model. Here comes a question. Why is this nonlinearity so important? If we use a linear activation function instead, no matter how many layers we stack, the entire network would essentially behave like a single layer. This would limit its ability to learn and solve complex problems. Let's continue the forward propagation. The hidden layer outputs become inputs for the output layer. We repeat the weighted sum and activation function again and get the final output. After the forward propagation, the neural network outputs the predicted value. We are going to use this cost function and quantify the difference between the predicted output and the actual target value. Based on the cost function, the network can adjust its weights and biases to minimize the cost. In order to do that, we need the backpropagation. Based on the cost function, the goal of backpropagation is to compute the gradient of the cost function with respect to each weight and bias in the network. Then simply update weights and biases with a certain learning rate. When we train in the neural network, forward propagation helps us find out the error made by the current weights and bias. Backpropagation updates weights and biases in order to reduce the error. By repeating the process many times, we can improve the neural network predictions accuracy on the training set. Before diving into the backpropagation, we need to understand the basic calculus first, the chain rule. It allows us to compute the derivative of a composite function. The neural network essentially is composed of many functions together. In order to calculate the gradient of the cost function with respect to each weight and bias, we need to apply the partial derivative of the cost function with respect to each of them. The chain rule is a formula for computing the derivative of a function that is composed of other functions. If a variable y depends on the u and u depends on x, the chain rule states that the derivative of y with respect to x is a product of the derivative of y with respect to u, and the derivative of u with respect to x. Get back to our neural network example. Let's apply the chain rule to calculate the gradient of the cost function with respect to W5. There are three intermediate functions. The cost function dc over dw5 equals multiplying with all the derivative of intermediate composite functions. dy3 over dw5 multiply with da3 over dy3 multiply with dc over da3. Similar to W6, this is the gradient of the cost function with respect to W6. Now, let's apply the chain rule one layer before. It is similar to W5, but the path is longer and involves more intermediate functions. We simply add more composite functions derivatives. And this applies to other weights. You might have noticed that these two parts are the same. During the backpropagation process, we can catch a result and avoid duplicate calculations. It allows us to compute the current partial derivatives by simply reuse the previous layer calculation results. It is a very smart part of backpropagation. If you're still confused about the backpropagation calculation, don't worry. Let's take a closer look at the partial derivative of W5. The left-hand side are all the individual functions. The result of dy3 over dw5 is the output of the previous neuron, A1. dA3 over dy3 is the derivative of a sigmoid function. We can plug y3 into this formula. The last part is the cost function, and this is the derivative of the cost function. We need to multiply them together and get the final partial derivative of W5. Let's take a closer look at the partial derivative of W1. d11 over dw1 is the input feature x1. dA1 over dy1 is the derivative of the sigmoid function with the input y1. dy3 over dA1 is a W5. The rest two parts are exactly the same as the previous slide. Now, we fully understood about forward and backward propagation. The following slides visualize the learning process of neural networks. We will feed the same data into the network repeatedly, allowing us to observe how the network improves after each iteration. Especially, we will see how the network adjusts its weights to minimize the cost function and reduce the prediction errors. The inputs x is 1 and 2. W hidden and W outputs are randomly initialized. A is a prediction of the neural network. Y is the actual target. We set the learning rate as 0.5. As you can see, each iteration, weights are updated accordingly and the prediction is closer to 1. At the 99 iteration, the neural network outputs 0.91, very close to 1. Now we have finished all the theories behind the backpropagation. The actual implementation of this simple neural network should become very easy. Here, we initialize the learning rate with 0.5, randomly initialize W hidden and W output. We are going to use the matrix format. W hidden stands for the 4 weights at the first layer. W output stands for the 2 weights at the second layer. The sigmoid function and sigmoid derivative are utilities functions. The forward propagation function follows the same process we have mentioned. First, use the input matrix X dot product with W hidden. Then we apply the sigmoid activation function. Then we use output from the hidden layer A1 dot product with W output to calculate Y2. Then applying the sigmoid function on Y2 to calculate A2, which is the output of the forward propagation. We need to return this value so that we can catch them during the process of the backpropagation. Inside the backpropagation function, first, calling the forward propagation, dA2 is a derivative of the cost function. dy2 is a sigmoid derivative of the activation function in the output layer. Partial derivative dw output equals output from the hidden layer matrix product with dy2 multiplied with dA2. This part of the code is exactly the same as the partial derivative we have discussed already. Now, we have partial derivative of W hidden and W output. Update this W hidden and W output by a partial derivative multiplied with the learning rate. I have printed the prediction for each iteration. As you can see, our neural network is learning from cost function and makes the prediction gradually close to 1. If we change the prediction label to 0, our neural network updates the weights and makes the prediction gradually closer to 0. The actual implementation should include the bias term in each neuron. It should be simple. We need to add another bias matrix and include it in each forward and back propagation. This code is a skeleton of simple neural network implementation. It helps you understand the concepts. The most important thing is to really understand how the neural network actually works. The actual implementation becomes easy after you fully understand what we have discussed during the slides session. Always feel free to play around and customize it to better suit your learning goal. This is the end of the video. I hope you have a better understanding of backpropagation and the fundamentals of neural networks. If you have any questions, please leave in the comment below. Please consider like and subscribe. Thanks for watching, and I will see you in the next video.